So, according to clause 5.2 EC3 part 1.5, shear buckling resistance is given as VBRD is equivalent to what you can see here in this red box. And where the contribution from the web is given as what you can see in this box, VWRD is represent for the contributions from the web, whereby VBFRD is represent the contributions from the flange. So this check should be carried out for every panels. So what does it mean by every panels? Every panel means, if you can see here, this is our plate girder earlier, whereby we have 20 meter in length and we have a transverse stiffness located at 1.2 meter, 2.55 meter, 4.15 meter, 6.25 and 10 meter, which is this vertical line represent the transverse web. So every panel means you need to carry out the shear buckling resistance, because you need to check that all these panels can satisfy the condition given. Okay, so this means what I mean by the panels, which means the area between A and B is considered as panel AB. Area between B and C is considered as panel BC, and similar goes to the other panels. So, before you carry out the shear buckling resistance check, I would like all of you to come up with this table. Okay, if you look at this table, you have the parameters and panel A, B, B, C, C, D, D, E, and E, F, which means this panel, as I said earlier. So, for each panel, you need to define what is the distance from support A, panel width, moment, shear, C value, reductions, the factor for the buckling, flange-induced buckling, slenderness ratio for the web, and the shear buckling resistance. Okay, so I will show you how we can fill in this table later, but now we will continue with how to conduct the shear buckling resistance check. Okay, now let's look at the requirement for the shear buckling resistance. And bear in your mind that the examples that I wanted to show here is for panel AB. As has been told you earlier, that we need to carry out the shear buckling resistance check for every panels. Okay, so now we are doing for panel AB. Okay, so this is the requirement, and VED is represent for the maximum design shear force, whereby VBWRD is represent for the web contributions, VBFRD is represent for the flange contributions, and it must be lower than the requirement given in the Eurocode. Okay? Alright, now let's look at the first part, which is flange contributions. As we can see, we have web contributions and the flange contributions. For the shear force, we already found it. Okay, so let's settle the flange contributions. So for the flange contributions, you can get it from clause 5.4. You can refer to this clause, EC3 part 1.5. So when the flange resistance is not completely utilized in resisting the bending moment, okay, the contribution from the flange should be obtained as what you can see here. So in these equations, BF, TF, FYF, you already know what it is. And gamma M1 is what we call as the aspect ratio. So what is C value? Okay, C value is given by equations, whereby if you can see the C value, it is equivalent to C equivalent to A 0.25, all right, plus 1.6 BF TF squared FYF and then divided by THW squared FYW. Okay, so C is equivalent to these equations, whereby MEV is the moment which is you measured at 1.2 meter from the support. Why 1.2 meter? Because your panel AB, okay, whereby you have the stiffness located at 1.2 meter. So in this case, you have 1.2 meter. So maybe you will ask, so how about if you are calculating at panel C? If you're calculating at panel C, so the length is 2.55 meter. So in that particular case, your cutting section must be longer. Okay, which means if you have this is your load, and then you have MED. So for panel, so this one A, B, and you have another panel, panel C. So for panel C, so meaning that you have a 2.55 meter, and the reaction support is 2320 kilonewton. So that is how you find, okay, kilonewton per meter if you are doing for panel BC. So for panel BC, the length must be larger, which is 2.55 meter, because you have another panel, or sorry, you have another transverse web stiffener at 2.55 meter from the support. This is the support. Okay. All right. All right, so now you know what is C and you know what is MED, because those are the parameters that we need to find to complete the check for flange contributions. Okay, so let's go to the next one. So in this particular case, you need to find what is your C. C has been explained earlier. This is the formulation of C. Nothing to worried about, because most of the parameters that we have here, we already have it. Just insert in the C value, and finally you will get C is equivalent to 325, and this value you substitute in these equations. So for MED, how you wanted to get MED? Okay, for MED, this is how you calculate MED. Okay, so for MED, you can see this is a cutting section, which is this is a panel A, B, which is calculate this. You can see this is the cutting section from A to B, all right, with 1.2 meter, 2320 MED, and the loading is 232 kilonewton per meter. So by taking the equilibrium forces, submission moment at 1.2 meter, okay, positive equals to 0. So then 2320 times 1.2 meter, okay, minus 232 times 1.2 divided by 1.2 divided by 2. So once you calculate it, and then you will get 2617 kilonewton meter. And this value, you need to substitute in the equations VBFRD. Okay, you substitute in the equation VBFRD, and C value you already got it, and you insert it already. So then you calculate the whole equations. Finally, you get 619.2 kilonewtons. So then you know that your VBFRD, okay, your VBFRD is 619.2 kilonewton. Okay, so we now know that our flange contributions forces is 619.2 kilonewtons. So here we can say 619.2 kilonewton. All right, so next we need to find what is the web force contributions. Okay, web contributions. So to find the web contributions, okay, to find web contribution, this is the equations where you can refer to clause 5.3. and table 5.1 clause 5.3 EC3 part 1.5. Okay, so this for clause EC3 part 1.5, you need to find, the first thing that you need to find is the value of the web contribution factor. So to get the web contribution factor, you must refer to table 5.1 clause 5.3 EC3 part 1.5. For the contributions of the web to the shear buckle resistance should be obtained from this table. Okay, so there are two conditions in table 5.1 as you can see. The first one is the rigid end post and the second one is the non-rigid end post. For in our case, we are designing the non-rigid end post. So therefore, we need to clarify whether the reduction factor, the contribution factor, is fall within which categories, or it comes from these categories or the other categories. So once you get those categories, you can refer to clause 5.3 EC3 part 1.5 figure 5.2. So in this figure you can see there is a reduction factor and lambda W. Okay, lambda W is the slenderness web ratio. If you can see, the graph 1 is represents for the rigid end post and graph 2 is represent for the non-rigid end post. Lambda W in figure 5.2 can be obtained by using equation 5.3, in which the parameter tau CR is equivalent to equation 5.4. Okay, now let's refer to table 5.1. So if you look at table 5.1, our condition is the non-rigid end post. So for the non-rigid end post, firstly, we need to check whether the slenderness parameter is lesser than the 0.3 over end mu or not. So in this particular case, what is the value of this parameter? Because recall back, in this case, your grade of plate girder is S355, which is lesser than S460. Because of that, your parameter nu is equivalent to 1.2. And substitute those equations, those value 1.2 in the equation given in table 5.1, which hence give you 0.69. So which means 0.69. So you must to check whether 0.69, you must to check whether 0.69 is lesser than lambda W or not. Okay, because if you refer to table 5.1, you need to make sure that the 0.83 over nu is larger than lambda W or not. So now our next task, we need to find what is the value of lambda W. Okay, so again, to recall back, lambda W equations is given in clause 5.3 EC3 part 1.5, equations 5.3. So if you look at the equations, this is the equations given in equation 5.3. So here, you know what is your yield strength for web, which is 355. But what is this? Tau CR. Tau CR is given in equation 5.4, which is equivalent to K tau times with the stress E. So students, so now we know that the slenderness parameter is come from the equation 5.3 and this is come from equation 5.4. So the only thing that we need to find is this parameter. So we do not know what is this parameter. So we need to calculate, which is equivalent to these equations. So here is being calculated before. If you can still remember, when you calculate for this, Okay, when you calculate for the checking on this slenderness parameter ratio, you have calculate this value. Okay, this value is depends on A over HW. If it's less than 1 or it is more than 1. I hope you still remember on this. Okay, but in our case, we already calculated and we get 17.8. Okay, so we got 17.8 there, but this value is represent this. Okay, so here, what is your T, what is your B? All right, so here you can see that T is represents for your thickness of web, and B is represent your height of the web. Okay, your height of the web. B is the height of the web. Okay, and T is your thickness of the web. So you insert this into equations. So finally, you will get 73.5 Newton per millimeter squared. So this value you can insert back into the lambda equations and you will get 1.67. Okay, and then you will get 1.67. So if you refer back to your table, okay, if you refer back to your table 5.1, you can see that 1.67 is larger than 1.08 because it's not fall under the middle category. It is fall under the last category, which is the slenderness parameter is larger than 1.08. Therefore, when you refer to table 5.1, in the condition where your lambda W is larger than 1.08, for the non-rigid end post, the contribution from the web is given by these equations, which is 0.83 over lambda W. You can insert the value that you'd find for the parameter contribution from the web into this equation, okay, which give you 0.5, insert the value, and finally you will get 1780.1 kilonewton, which is represent the force contributions from the web. So now we already have the force contribution from the web is 1780.1 kilonewton. Okay, so in this particular case, you have those values. So then finally you need to calculate for this value. So for that value, okay, basically all the parameters here, we already know the value. So here is 1.2, insert all the parameter, and finally you get 4272 kilonewtons. Once you get the 4272 kilonewtons, you are now can substitute all the equations, forces that you already calculated, whereby 1780.1 plus 619.2 is lesser than 4272. So you finally found out that 2399.3 is larger than 2320 kilonewton, but lesser than the allowable shear buckling resistance. Thus, for panel AB, okay, for panel AB, you are now confidently said that it can resist the shear buckling resistance because it has complied those equations. Okay, it has complied these equations. This is larger than VED and lesser than the allowable shear buckling resistance. Okay, so we have complete the shear buckling resistance check for panel AB. Okay, so now as I showed you earlier, you need to come up with this table. So in this table, we have summarized that distance from support for panel AB is 1.2 meter, panel width 1.2 meter because this is the distance of the panel width. All right. And then moment, MED, is 2617 meter. Shear, VED, is 2042 kilonewton. C is 335. The contribution factor for web is 0.5. The slenderness parameter lambda W is 1.67. And finally, you will get your shear buckling resistance by taking into considerations the contribution from web and flange. You get 2399, which is acceptable. Okay, so next task is your job, students. So what you have to do, you have to complete all the other panels. So if you look here, we still have the remaining panels, which is B, C, C, D, D, E, N, E, F. Okay, so next, you need to continue with a simple exercise to check the shear buckling resistance for every panel. Okay,